Okay. So to briefly review chapter 2, well, there's two types of logic, combinational and sequential. Combinational is memoryless, sequential has memory. Chapter 2 is just about sequential logic, so when we get to chapter 3, we'll be covering, chapter 2 is about combinational logic, right? And we get to the next chapter 3, it'll be about sequential logic. So there's some terminology. We talked about sum of products and product of sums. Sum of products is when you have a truth table and you want to build a logical expression that behaves behaves according to the truth table, right? You go through and you find all of the outputs that are true, right? And you for each one of those, you construct a minterm. The minterms are a combination of all of the input literals that correspond to that minterm. So if there's a 0, then that would be a negated form of the input, and 1 would be the regular normal form of the input. So in this case, this minterm, this is the first minterm, reading from the top down, and this would be not A and B, and this would be A and B because they're both 1, right? Sum of products. So that was sum of products, right? Product of sums is when you look for the zeros instead of the ones in the output, and then for each one of the zeros, you construct a max term, which is the sum of the input literals, but you have to negate them. So this would be A is 0 and B is 0 here for this first row that has an output of 0. So this would be not A or B, right? Not A, A or B. It wouldn't be not A, scratch that. It would be A because A is 0 here, but we would negate it when we create the max term version of it. You guys with me? I confuse everyone there. So this would be A or B, and you'd find the next max term would be the next 0, and so this would be not A or B, right? Everyone with me? Okay, so why would who cares? What's the point of all this? Well, you might want to choose to use product of sums or sum of products depending on whether there's more zeros or more ones in the output row. So if there's more ones and less zeros, it might be a little bit more resource efficient to use the product of sums, right? Because the product of sums, you would have one max term for every 0 output. And if you have less 0 outputs, that would be beneficial, right? You guys with me? Okay. Yes?
So what's with the formula at the bottom? Y equals?
Oh yeah, so this is what I just said. This is A or B, right? That corresponds to this first max term, the first 0, right? And this is the second one. This is not A or B, right? That's the next max term. And again, you have to make sure that this is easy to forget, so you have to be careful here. But when you build the max terms, you have to remember to negate the literals with respect to the way they appear in the input columns of the truth table. Does that make sense? Okay, so like if I go back to this example, this was the sum of products. So these were the min terms. So we were looking for the ones, and we did not negate these. So this was not A and B. Not A. Oh, that's odd. That must be a typo. Oh, actually, I know what happened. The not got moved. I have to fix that. That's a bug in the slides. I'm glad I looked at that. Can you see that little bar right there? That bar was supposed to be above. Somehow that got moved. Yeah, so that should be not A and B. So not A and B, or A and B, right? So those are your two min terms. not negated, right? But the max terms are negated, and that's because the idea is that when you build, the book doesn't show this, but what's really happening here with sum of products is that when you build these max terms, originally you build them as products, right? So you say not A and not B originally, but then because that's the negated form of the output, you apply De Morgan's law, and De Morgan's law will convert the and to an or, and it will negate each of the literals, well, the variables, right? You with me on that? So like you start out with A, not B, or A and not B, right? That's because you have to, you're looking for these combinations of states that give you a 0, right? But then because that you're doing that for the 0 rows, you have to negate the whole expression, in which case these, because of De Morgan's law, these, well, actually what happens is that this, you start out with the top level or, right? That becomes an and, right? So you still end up with not A, not B, but that's negated, right? And then this becomes an and, right? And then this is A and not B negated, right? And then, so that's the first De Morgan's law. And then you apply De Morgan's law to both sides. So this becomes A or B, right? Negating the individual A and B there. And then this is not A, B, right? So that's how you end up with your, sorry, there you go. That's how you end up with your product of sums. Make sense? The book doesn't go through that whole process. It just says you, whenever you do sum of products, look for the zeros and then negate the inputs.
What from the line makes it a 0? Why is 0?
Well, it's just, well, that's just, in this case, it's just an arbitrary, randomly generated function. It depends on what you're doing. Like if you were building an adder, then y would represent the sum. If you were building a control unit for the CPU, y might be a control signal, but it would depend on what you're doing, what the application of the circuit is. In this case, it's just a general, there's no specific application. It's just a general circuit. Okay, here's an example. I think that, actually, to answer your question, the book actually has an example where you build a circuit for a specific application. In this case, it's deciding whether you're going to eat lunch. All right, so they kind of construct it as an actual an example of something. Okay, so we talked about the axioms and the theorems. Axioms are just the definition of what an and an or operation and a negation are, right? Theorems are useful for taking a Boolean logic expression and converting it into some equivalent form. Why would you want to do that? Well, you might want to minimize it, or I showed you an example in the last class where our goal wasn't to minimize it, but our goal was to transform it in a way where we could map it. When I say map it, like implement it as a circuit where the gates have no more than, say, 2 inputs. You guys with me? Does that make sense? So you can apply these theorems to change the expression into an equivalent form that gives you the same, and when I say equivalent, I mean a form that would give you the same truth table, that would be true under exactly the same conditions and false under the same conditions, right? So for example, there's the identity theorem that just says if you have a variable and you AND it with 1, it's just equivalent to that variable, the original value of the variable. So b and 1 is equivalent to b. B or 0 is equivalent to b because if you or anything with 0, you get the original value. Then there's the very similar to that is the null element theorem, where if you and any variable with 0, you're guaranteed to get 0 out. Likewise, if you or any value with 1, you'll have a 1 result, 1 output. By the way, sometimes I say true and false. Sometimes I say 1 and 0. You guys, yeah, don't let me confuse you with that. Idempotency theorem. Also kind of similar. If you and a variable with itself, you get the original value. Or if you or a variable with itself, you get the same value. Involution. By the way, there was a typo on the original version of the slides. The title here was wrong on the original version. I corrected that. This is the involution theorem. If you double negate a variable, it's equivalent to the original variable. So these are fairly obvious, these first few anyway. Complement is if you take a value, a variable, and you and it with its complemented form, you're guaranteed to get 0. So the idea is if the original variable was true, then you're going to and it with false. Or if it was false, then it doesn't matter, because anything you and it with will give you a false or a 0. Likewise, if you have a variable and you or it with the negated form of itself, you're guaranteed to get 1. Okay, so those are pretty easy to follow. Then they get a little bit more complex. So you have commutativity and associativity. Commutativity is, I always remember this, CO, by thinking of the first 2 letters here, CO, as meaning change order. So this is like changing the order. You can, both the and the or are commutative. The order in which you perform the operations doesn't matter. Associativity is when you change the evaluation order. So in this case, they have B and C and D. And so if you can do B and C and then take the result, the intermediate result of that, and then and it with D, and it's equivalent to performing the C and D first, and then anding the intermediate result with B. Then distributivity, this one comes up, this is like probably the most common one you'd use if you were manipulating these expressions. It works the same way, well, at least this one does. This one on the left here works the same way as it does in algebra, where if I have B and if you think of and, of course, as like a multiply, and then C or D, right? You think of or as an add, then the B will distribute over C and D. So this is equivalent to saying B and C or B and D, right? Makes sense, right? Now the weird part about this, though, is that if you look at the dual form, where we're swapping ands and ors, so each of these has a dual form where you've got an and version and an or version. This one's kind of strange because this says B or C and D, and you can distribute the B over C and D, even though the operators look like you can't do that, right? Because this is like an add. Like this wouldn't work in algebra, but it works in Boolean logic. You guys with me? Okay, so those aren't too bad. Then they get really strange. You got combining. Now this is not obvious when you look at it, but B and C or B and not C is equivalent to just saying B. Why? Well, because regardless of what C is, you'll end up just anding both it and its complement with B, so it's equivalent to B, right? That was combining, right? Yeah. And then covering is similar idea. In this case, if you have B and B or C, if B is 0, then the whole thing is 0. The whole expression is false, right? If B is 1, well, then it doesn't matter what C is, right? Because you're ORing B with C, and B is 1. So it's kind of this is kind of redundant, right? But you wouldn't know that. It's not obvious from looking at that's the case. But that's how it'll work out. Everyone with me? Yes.
So
No, no. No, because the reason is because the questions I plan on asking, you can achieve this same stuff using Karnaugh Maps, which I'm going to get to in a bit. Consensus is I won't even bother. I'll come back to that once we get to Karnaugh Maps. Okay, so we went through these examples, and then we also talked about this idea of bubble pushing. This is if you have, there's a question on the quiz about this. The idea is if you have a circuit with these negated gates. Now you might say, why? Why would you have that? Well, remember, CMOS gates are all negated gates, right? You guys with me? CMOS, which is the process by which all modern gates are made. So if you're looking at an implementation of a circuit in an actual chip, they're going to be these negated gates. If you want to convert this to a form that is more conveniently expressible as a Boolean expression, you use this bubble pushing concept, which is where you basically just apply De Morgan's law backwards from the output towards the input. So for example, in this case, let's say this was your last gate, because Y is your final output, right? You can take the bubble that would inevitably be on the output of this gate, because we're using all negated gates, and you can push it backwards by taking the bubble off the output, putting it on the inputs, and converting the gate to an OR. That just applies to Morgan's law, right? Now you might say, well, why in the heck would I do that? Well, the reason is because as you work your way backwards from there, so I've done that to this gate. As you work your way back, you'll notice that, for example, here, I've got a bubble on this input, and it's connected with a wire to another gate's output that also has a bubble, so these two bubbles cancel out. You guys with me? Right? So the effect of that is that it turns this into a regular old AND gate, which is nice, right? It's convenient. Also, this gate, well, at least half of it turns into a regular OR gate. The other half is connected to D, but then we can just say, well, we'll just make this not D, in which case we can cancel out that bubble. You guys with me? Right? Okay. So you just keep applying that, and the book doesn't carry this through all the way to the end, but, well, actually, what the idea is that this bubble stays, but it negates this D. So when you write the expression out, the D becomes negated, right? Likewise, A and B are both negated here. You right with me? Now C doesn't get negated because I didn't have to, because I didn't have to push the bubble through this gate, because that bubble got canceled out, right? The output. So this AND gate, this NAND gate, stayed as an AND gate. Does it make sense? Okay. All right. So all right. So so later on in the semester, we're going to be looking at a lot of circuit diagrams, circuit schematics. So so far we've looked at a lot of Boolean expressions and truth tables, but as time goes on, we're going to be transitioning more into looking at circuit schematics. And so you have to get used to the idea of reading circuit schematics. So they introduced that concept in Chapter 2. You've got schematics are essentially just gates and wires. Sometimes they're called netlists, is another name, or block diagrams sometimes. But the idea is that it's made to look like a circuit. Now, the thing that used to confuse me when I first started looking at these logic circuits was I was taking my circuits classes in electrical engineering at the same time. So I was literally in one semester, I went from one class that was a circuit in electrical engineering that had resistors, capacitors, and inductors in it, and it had actually had a circular structure. Then I'm looking at circuits over here, and there's no circular structures. They're all just kind of linear, sequential. I'm like, what's the What's the deal? How can you call these things a circuit? Well, they're still a circuit, but because we're abstracting out the transistors and we're looking at it in terms of gates, you don't see the actual circuit. You don't see the power and ground wires, right? You don't see the pull-up and pull-down networks. If you were to take these, well, I'm not showing any gates on here yet. Yeah, like here. Like if you take one of these type circuits, there's still a circuit, but it just abstracts out the actual analog circuitry part, right? Okay. Anyway, there's different conventions for drawing circuits. This is not really standardized. In this book, they say that if there's a T-junction, the wires are connected, right? And if you have two wires that intersect, they're only shorted together if there's a dot. Otherwise, they're not connected. That makes sense? Different books and different people will use different conventions for this. Okay. All right, so let's switch topics again here. Let's talk about multiple output circuits. So this is a priority circuit. What's special about this? Well, it's got more than one output. Every truth table we've looked at so far had inputs, multiple inputs, and one output column. This has 4 output columns, right? The idea is that you're calculating separate results, separate outputs from the same inputs. It's from the same set of inputs. You guys with me? So what's happening is that you've got these 4 inputs come in, and some of them are going to be fanned out, like split off and connected to different gates, which ultimately may be generating different outputs downstream, down the line. You guys with me? So in this case, they draw a line to separate, to make that obvious. They separate the inputs and the outputs. This is a priority circuit, just means that we have 4 outputs, but in this application, all the outputs are 0 except for 1. And the one that's not 0 represents the position of the furthest to the left input 1 bit. Does that make sense? Right? So like for example, there's no, in this first row, there's no 1 bits here. Second row, there's 1 bit, and it's all the way to the right. So A0 is the furthest to the left 1 in the inputs, and thus we mark Y0 to 1, right? Over here, A2 is the farthest to the left input, so Y2 is the value that we assert. Okay? So you can implement this in a circuit like this, surprisingly. So Y3 is just shorted to A3, right? There's no gates at all. It's just a direct connection. It's shorted. Y2 is an AND with a bubble. Now this is kind of a strange way to show this, but instead of putting an inverter here, they just have a bubble here on A3. So they're negating A3 and not A2, and then ANDing those values to get Y2, right? And then Y1. So the idea is that if A3 is 0 and A2 is 1, then Y2 will be 1. Every other case will be 0. Okay, you guys with me? Okay. Okay, so another thing you can do is to simplify a truth table like that, you can use don't cares. You guys remember you guys covered don't cares? You might not have covered them like this though. You guys might have looked at don't cares in 211 for outputs, right? So sometimes you have an output that's a don't care, right? And if you do, you can use that to help you minimize the circuit. But don't get confused here. These are inputs that are on, these are don't cares that are on the inputs. This is a little different. If you have don't cares on the inputs, this means that this is just a shorthand because you would have to, it's essentially saying that I'm collapsing all of the rows in which all of the don't cares in this particular rows are expressed under every combination. Make sense? Right? So this would be 0, 0, 1, 0 and 0, 0, 1, 1, right? Over here, so there would be 2 rows. So because I have one don't care as an input, this would match up to this thing. This row with this one don't care input would get expanded into 2 rows, right? The next one down has 2 don't care, so this row would be expanded into 4 rows. You guys with me? Does this help us simplify this circuit? Not necessarily. It's just a shorthand, right? But that's because, again, that's because the don't cares are on the inputs, not the outputs. Okay, so later on in the semester, we're going to be covering HDL once we get to, I guess, chapter 4 or 5. This is when you want to design large-scale digital logic circuits. You write code in what looks like a high-level language. It is a high-level language, Verilog or VHDL, and it gets compiled and synthesized into gate-level designs, schematics, right? And then you can simulate it. The problem is when you're simulating this stuff, the purpose of simulation is to debug the designs, right? And so there needs to be a way that the simulator could mark the value of signals to draw attention to signals that are bugged for whatever reason. You guys with me? So like instead of just having 0 and 1 for a binary value, they introduced this x, right? And x is, it means there's a problem. But it's also a third value that a signal can take on when you simulate your circuit. And there's actually there's 3 reasons why you would have an x in there, right? The most serious one, the one that causes the most issues is contention, where whenever you have a signal, notice, by the way, yeah, so notice you have like these input values are fanned out. You know, this A3, for instance, is connected to this output, it's connected to this gate, it's connected to that gate, it's connected to that gate, right? So this one wire fans out to multiple places, right? Make sense? But you have to be careful that if you look at the output of a gate, the output, each wire can only be driven by one gate output, can only be connected to one gate output. I have a better example. Let's see. Yeah, so for example, on this circuit, I could, for instance, I could take the output of this gate and I could connect it to other gate inputs. That's fine, right? In fact, that's very common, right? I could take the top level inputs and connect them to multiple inputs, right? But what you have to make sure that what you never do is connect the output of a gate to a wire that's also connected to another output of a gate. Does that make sense? Why is that? Because if you remember from the when we looked at the CMOS gates, you have a pull-down network. Every gate output is connected to a pull-down network and a pull-up network, right? The pull-down has NMOS transistors. The pull-up network has PMOS transistors. And so the idea is that every combination of inputs will always turn off either the pull-down or the pull-up network and turn on the other one, right? You guys with me? The problem is if you have 2 gates that are both connected to the same output, if you short the outputs of 2 gates together, and if one gate tries to pull up, like tries to output a 1, and the other gate tries to output a 0, you end up creating a low impedance path between power and ground, because you create a connection where you've got one net, one signal, one wire that is both connected through to the VDD rail through one gate and to the ground rail on another gate, right? So you basically just short out your power and ground, and that'll destroy your chip, right? So when you simulate and you see an X, that usually means that you have, they call it contention in the book. I always called it double driving. It means you're double driving a wire in your design, right? This with me? And you might think, well, how easy could it be to do that? Well, it actually is pretty easy once you start writing code in Verilog. We'll get to that a little bit later. The other reason you might have an X is if you have a value that's undefined, which they don't talk about here because that's something that will be addressed in the sequential logic section. But if you have a memory or a flip-flop or some kind of memory element and it hasn't been initialized, and you go to simulate the circuit, the period before you initialize that memory, you get X's. That just means unknown, right? Doesn't know what it is, right? In reality, it would come up as a random value. But in a simulator, they mark it as X, so it draws your attention to that. And then finally, you can also use X when you actually set a signal as an X. As an output of a circuit, like where you have a circuit, you explicitly say X. That means it's a don't care output, right? So that's your way of telling the synthesizer tool, the compiler, that it can use that don't care to do some optimization, right? To minimize, to reduce the resource usage of the circuit potentially, right? Use that to its advantage in the optimization. You guys with me? Okay. There's also this Z that comes up. So Z means high impedance. Z is used when you have a wire in your design that's floating, meaning that it's not being pulled down. You don't have any gate that's pulling it to ground, and you don't have any gate that's pulling it up to VDD. It's just floating. This is something that you may want to do if you want to create a shared bus. So I mentioned that you can't have two outputs, two gates driving the same wire, right? You don't want that because if you do that, you'll have an X in your simulator, and if you actually make a circuit that does that, it'll burn up. But what happens if you want to have multiple modules, multiple gates that can potentially write to the same wire, but not at the same time? Well, then you would use these things called tri-state buffers, which is, it looks like a buffer or like just a triangle with a control input on it. And the control input, in this case E, is going to control whether I connect Y to A or not. If E is 0, then Y will be Z. And if E is 1, then Y is just whatever A is, whatever value A happens to be, right? Why would you do this? It's because this allows you to have, you can have multiple tri-state buffers all connected to the same physical wire as long as only one of them is sending out an actual 0 or 1 and all the other ones are Z, then you can create this, I think there's a picture, yeah, you can create this shared bus, so it would look like this. So this is kind of a bad example because in modern chips, they wouldn't use a shared bus for this anymore. They would use a switched network on chip. They'd use a switched interconnect. But you still use these things for smaller scale systems. But anyway, this picture is showing processor, video controller, Ethernet controller, and memory all connected to a shared bus. But when they drive it, they all drive the shared bus through a tri-state buffer, right? And only one of them will be setting that to 1 or 0 at a time. Make sense? All right. Okay, so let's quickly review Karnaugh Maps. You guys remember Karnaugh Maps? How many of you remember Karnaugh Maps really well? Okay, about half. So you guys covered this pretty well in 211. That's good. Okay, well, I'll go through this fast then. Karnaugh map, it's basically just the truth table, just represented in a different way. In this case, this is 3 inputs, so you have, there's 3 inputs, so there needs to be space for 8 output values, right? The way you generally organize these, if you have 3 inputs, is you have 4 columns, 2 rows. You could do it with the other way, though. You could transpose this if you wanted to. The columns are, in this case, A and B. The rows are C. The 4 rows represent the 4 possibilities for A and B's values. Likewise, the 2 rows represent the 2 possible values of C. And then for A and B, because there's two variables here, you use gray coding where you only change one as you go from row to row. So 0, 0, 0, 1, 1, 0, 1, 1, right? So each one of those entries in there represents an implicate, actually a minterm, and they're shown here. So so in this cell you've got A, B is 0, 0, C is 0. So this is not A and not B and not C. Right? And so the idea is that when you take the truth table and you convert it to the Karnaugh map, you read the inputs. So in this case, y is true when A, B, and C are 0. So because I've labeled A and B are the column headers, I got 0, 0, and 0. C is 0. So I go 0, 0. I got column 0, 0. C is 0. So that's row 0. And then I would mark that guy as 1. And then the other minterm is 0, 0, 1, so A and B is 0, 0, and C is 1, so I'd mark that as 1. Everyone with me? All right. OK, so you can minimize these by grouping together adjacent ones. And your goal is to create these implicates where if you circle these 2, A and B are both false, and C is both true and false. So as such, C is redundant in this case. So I can minimize that out. And these bars should be above A and B. Need to fix that too. Sorry. Any questions? I'm going fast because it seems like everyone's pretty comfortable with this stuff. It's another example where you've got another truth table. In this case, I've got 3 1s in there. So I will find where do those 1s go. So I got 3 1s in there. I got to put them in the K-map. So 0, 1, 0. So 0, 1, 0. So 1 will go here. 0, 1, 1. There'll be another one here. And 1, 1, 1. There'll be 1 here. So it should be these 3, right? Yep. Or did I screw that up? 0, 1. Yeah. 0, 1, 0, 0, 1, 1, and 1, 1, 1. Oh, that's interesting. That 1, 1, 1. Huh. I just noticed that. That must be a bug, right? Should be 1, 1, 1. That should be a 1 right there, right? Am I right? OK. OK, so anyway, in this case, I'm going to circle these 2 guys. Well, in this case, I mean, assuming this were right, I would circle this group and that group. You guys with me? Right. Yeah. Now, by the way, earlier I was talking about those Boolean theorems. I mentioned the one called consensus that I skipped over. If I'm not mistaken, we've just, this is consensus. Right? right? I think that's consensus. So the idea is that we've got, the reason I say that is because this 1 here is circled, is part of both implicates, right? As a result, in this case, I'm doing A and B or B and not C. But in either case, both of these are covering, this midterm 0, 1, 0. It's not that important. Okay. All right. So we got these, complement, literal. This is the same thing I presented at the beginning of the lecture. Implicate, just a product of literals. Prime implicate is, in terms of a Karnaugh map, a prime implicate is when you're finding it represents a grouping of ones on a Karnaugh map that isn't part of a larger grouping, that can't be made part of a larger grouping. You guys with me? So for example, if I had a 1 here, in addition to these 3 ones, I could circle all 4, right? And that would be a prime implicate. But if I had that and I only circled 2 pairs, those would be implicates but not prime implicates, because they wouldn't, each one of those could be contained within a larger grouping. You guys with me? All right. Okay, so you want to make sure that you circle every one at least once. Now, don't cares. Do I have an example of that? Okay, well this is a 4 input K map. Did you guys do 6 input K maps, by the way, into 11? So you can actually you can scale this up to 6 variables. This one has 4. Obviously, a 4 would be 4 columns and 4 rows. If you were to scale this up to 6 input variables, there would be 64 cells. So you'd have to have 4 of these 4x4 grids kind of in 3 dimensions, right? But you can do that. I don't think this textbook doesn't show any of those. The highest it goes is 4. But this also points out that Karnaugh maps are very limited. You can't go beyond. There's no way to go beyond 6 variables, as far as I know, right? Because you'd have to look at it somehow in 4 dimensions, right? So what do you do if you have more than 4 variables? You can't use Karnaugh maps. You have to use, there's some algorithms. There's an algorithm called Quine-McCluskey, which is an iterative algorithm that allows you to minimize Boolean logic that does not use Karnaugh maps. It just uses repeated application of the Boolean theorems, right? But Karnaugh maps are fine for going up to 6. If you have 4 variables, and this is the case, I've got A, B, C, and D. Some people, by the way, like to put A, B here and C, D here. It's just a matter of preference. Obviously, the locations of the way that you would map the truth table and the Karnaugh map would change if you do that, but it would be still valid. But anyway, this is a 4 input. I've got 16 cells, so 0, 0, 0, 0. So there's this guy goes here. 0, 0, 1, 0. So this would be 0, 0, 1, 0. The next one's down here, right? And so on. So you fill in all you should have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So all my 1s are in there. And then you circle your groupings. In this case, I've got, this is my favorite one. In this case, look, turns out that there's a 1 in all 4 corners, so you can draw a 4-element grouping that hits the corners, because the Karnaugh maps go around the edges, right? Go around the edges. They loop back. So in this case, the implicate that corresponds to the 4 corners is going to be what? Well, as you go from this side to this side, you're changing A, right? because A is 0 in this corner and A is 1 in this corner, right? Right? So you would have not B, right? And then likewise, if you look at the rows, C is changing, so you got just not D. So this four-corner min-term corresponds to not B, not D, right? Yeah, that's this one. So this one right here is your four-corner min-term. And then you've got this other one, not A. C is this 2 by 2. And then you've got two element ones that are these three literal min-terms. Everyone with me? If anyone's lost, by the way, I'm going through this really fast, just reviewing. If you're lost, please stop me, and I can go into more detail. OK, and then you can have don't cares, which is when you don't care what the output is. When would you not care what the output is, though, in reality? Well, for example, if you have input combinations that you would never expect to come up, right? Then you could just make the corresponding outputs don't cares, because you don't care because it'll never be relevant, because those inputs will never be set that way. Does that make sense? So if you have don't cares, then you can include them in your groupings if you want to. So in this case, because I had don't cares here, I was able to circle this huge group here, which got me just to C. Right? You guys with me? So you have to circle all the ones, but with the don't cares, it's optional. Alrighty. All right, so that's K-maps. I went through that super fast. If anyone needs more help with that, let me know. Or you can see me after class or outside of class. OK, so let's switch gears. Let's talk about some other basic building blocks of digital logic circuits. You've probably seen this too. Multiplexer. I can never remember how to spell multiplexer, because I can never remember if it's a multiplexer with an E or a multiplexor with an OR at the end. But anyway, it's a basic building block. Of course, you can build a multiplexer out of gates, but because they're so commonly used in digital logic circuits, they have their own special symbol. Looks like this little, well, usually it looks like a little trapezoid turned on its side. But if you guys remember from 212, they actually use an oval to represent multiplexers, which I always thought was odd. Hennessy and Patterson's architecture textbook is the only place I've ever seen a multiplexer shown as an oval. Everywhere else, it's this 90-degree hexagon, trapezoid type thing. Anyway, so the idea is that you can select, you have this select that allows you to essentially just short the output to one of the inputs, where the input you want to short it to is represented as the select. Like so in this case, you've got a 0 input and a 1 input. So if the select is 0, I want to short D0 to Y. And if the select is 1, I want to short D1 to Y. Make sense? So the select is kind of an address. You think of it like an address where you're addressing one of the inputs. So only one of the inputs can be connected to the output. Now, what happens if I want more than one output? Well, you can't do that with a multiplexer. But you can put multiple multiplexers together and form what's called a crossbar switch, right? You can have multiple multiplexers that all share exactly the same inputs, but separate outputs, right? That would be a crossbar switch. Any questions about that? So notice this truth table is kind of a weird form where they have S0, S1, and then the Y that corresponds to S being 0 and 1 is just D0, D1. So they just instead instead of expanding the whole truth table, they take this shorthand approach where they actually take the input D0 and D1 and they just plug it in there in the output column. Okay, so multiplexers can be built with gates, like I just mentioned. There's a few different ways to do it, though. One way to do it is to take each input. Well, in this case, I guess this is a special case, right? The two input one. So you've got two inputs. You associate an AND gate with each input, and then the select gets put into the AND gate with the input. Except for the first AND gate, you have the negated form of the select, right? So the idea is that if D0 if S is 0, then you want to basically turn on this AND gate, right, by putting a 1 in a second input. And that way, you'll pass through whatever D0 is. Does that make sense? Okay, and then likewise, the same thing down here. You've got S and D1 going into an AND gate. The problem is that you can't take both AND gates, you can't connect them to the same wire, right? Because you'll end up double driving that wire. So instead, they use an OR gate as a means to take the two intermediate outputs and merge them into one value, Y. You guys with me? So this is a way to fan in the inputs. You guys with me? I'm using this term here. This is a fan out, where you have a value you have one wire that's connected to multiple inputs. That's a fan out. And a fan in is when you have multiple wires that you want to reduce down to one wire. And so that you have to do that with a gate or a multiplexer. You can't just connect multiple outputs to one, but you can do it through a gate. So this is a fan in. You guys with me? Okay. The other way to build a multiplexer is through the tri-state. In this case, you've got two of these tri-states, and you have an input on both. You have D0 and D1 going into the input on two tri-states, and then both tri-states, in this case, you are double driving. Well, it looks like you're double driving the output, but you really aren't, because the tri-states, if you negate the input to one of these tri-states if you feed the negated form of S into the input into the select of one of the tri-states but not the other, you make them mutually exclusive, right? So if S is 0, you'll turn on this one and turn off that one. If S is 1, you'll turn off that one and turn on this one, right? And that way you can connect the output to one wire. You guys with me? Okay. And then of course, multiplexers in this case, this is actually a way that you can implement a truth table with a multiplexer by taking A and B. Now this is a 4-to-1 multiplexer, but if you take the inputs to the truth table and you make that the select, then all you need to do is hardwire each of the inputs to the multiplexer to build the truth table. So in this case, if the input is anything other than 1, 1, I want a 0 output. So I'll just connect 0. This is the ground. This little triangle represents ground, 0, logic low. So I'm going to connect the ground to the inputs representing the select to 0, 0, 0, 1, 1, 0. And this little T is the VDD, is logical 1, power supply voltage. Connect that to the 1, 1 input. You guys with me? I've got a question on the quiz about this, where you weigh the benefits of doing this versus using just gates to implement a truth table. And also there's another way to do it too, which is use decoders, and I have that in there too. I'll get to that in a second. Now, here, this is kind of neat because in this case, there's some redundancy here, because if A is 0, then it doesn't matter what B is. The output's 0, right? But if A is 1, then the output is a mirror of whatever the B is, right? So in this case, you can build a multiplexer by, you can build a smaller multiplexer. Instead of 4 to 1, it could be a 2 to 1. And then you would just hardwire the 0 input to ground, and the 1 input can be wired to B. You guys see that? Now, it's kind of ad hoc, right? They did this through, observing this behavior in the truth table. Everyone see that? All right. Now, by the way, when we get to, I want to point out here too, when we get to Verilog, which is the hardware description language, there are if statements in Verilog. No, it's not surprising, right? It's a high-level language. All high-level languages have if statements, right? Java and C, right? It's pretty standard. But the one thing that used to confuse me about that, it's like, how do you make an if statement in hardware? Like, how does that make sense? How can you write an if statement and then have that if statement converted into gates? I mean, that used to really confuse me. Well, it turns out this is how they do it. It's done through multiplexers. So this is the way, like if you write an if statement in a hardware description language, where you would say, if A equals 0, then Y equals 0, else Y equals B. That Verilog statement would get converted to this in hardware, right? Okay. All right, then we've got decoders. Hopefully, I think this is the last thing. Yeah, this is the last topic here that I think you guys will, that'll be just strictly review from 211. Decoders. Decoders are where you have a binary encoded input value, and you want to convert it to a unary, binary to unary conversion. What's unary? Unary is when you have a set of wires and they're all 0 except for one of them. Sometimes people call that one-hot encoding, right? I always call it unary encoding. So the idea is that you treat in this case, you've got 2 inputs and then 2 to that power outputs. So if you have 2 inputs, you have 4 outputs. If you have 3 inputs, you have 8 outputs, and so on. But you, again, just like with a multiplexer, you treat those inputs kind of like an address, and then that address determines which of the outputs is lit up, is set to 1, and the others are all 0. So if you put 0, 0 in, then the Y0 will be 1 and everything else is 0. But if you put 1, 1 in, that's treated like, well, what's 1, 1? Well, 1, 1 is the binary version of 3, right? And because of that, I will take Y3 and light it up, and the others will be 0. You guys with me? Now, what's so great about the decoders? I remember when I learned about this, I was like, okay, that's neat, but like, who would ever use that? Like, what is that useful for? Well, it turns out that decoders are used in every computer memory there is. They are the fundamental basis by which computer memory, all computer memory, DRAM, SRAM, flash RAM, all of them use a decoder because the memory address goes in and you've got a set of wires that come out that activate a memory cell for reading or writing. And also, when you learned about memory hierarchies, by the way, in computer architecture in 212, I don't know if they told you this, but they should have told you that computer memory always gets slower as it gets bigger. The bigger the memory, the slower it is. And when I say slower in terms of access time, the amount of time it takes to complete a read or a write operation, right? So that's the reason why we have memory hierarchies and cache. That's why Intel has gone crazy now. They've got 4 levels of cache. And now people are creating, NVIDIA is doing this thing where they've got this crazy high bandwidth memory that they're soldering on the top of the chip upside, in those multi-layer chips. And the whole purpose is to create this hierarchy of memories where you have smaller memories that are closer to the processor, and then they are backed up by larger memories that are farther away and that are larger, that are progressively larger. So this idea of memory hierarchy is really important, but the question is why? Why is it that bigger memories are slower? It's because of the decoders. Because the decoders, the bigger you make the decoder, the more outputs you have, the more stuff that has to happen inside there. And so they're slower. And this is, decoders are, fundamentally they're built with logic gates like everything else. And so, aren't there supposed to be bubbles on there? I guess I'm missing the bubbles here.
There's bubbles there. Or are you referring to the... Oh, I see.
I'm missing the bubble. Well, remember in the earlier slide, they pointed out that when you're reading schematics, this is what I get for trying to use the textbook slides. They pointed out that if you've got two wires that cross, they're not connected unless there's a bubble, right? One of these deals. The dot, right? Sorry, dot. I should have said dot. You're right. Yeah, so they don't have any dots here.
They only use T-junctions, though, for this diagram.
Yeah, that's why, you're right. Yes, exactly. They only use, and okay, so you're right. That's intentional because, for example, so this A0 is, you're right, there's a T-junction here that would connect A0 to this gate and A1. So this is A0 and A1. So yeah, you're right. Thank you for pointing that out. Yeah. So they're using T-junctions here to specify that. Okay, good. And likewise, Y2 is and A1 and with not A0. Y1 is not A1 and A0. Yeah, so thank you. You're right. They're all T-junctions. Okay, so this is the way that you can use a decoder to implement a truth table. It's kind of the same idea as when we use the mux, which is you take the decoder, you make the inputs come into the decoder, right? And then that is going to, each one of those outputs is going to represent your minterms. You with me? Right? And then, in order to select which minterms, you can just connect those to an OR gate, the ones that you want. I mean, so in other words, you take the outputs from the decoder, which will give you all the minterms of every combination of inputs, but then you would just connect the ones that that make up the actual minterms of the truth table or the Boolean expression, and you wire those into an OR gate. Does everyone see that? Yes.
Is that A and B and then A naught, B naught?
Yes, this is A and B, or not A and not B, or A naught and B naught. Yeah, that's right. Make sense? So this is yet another way that you can use that you can build an arbitrary logic function with in this case, a decoder. So I have a question on the quiz about this. I say if you can build it with a decoder or with a mux or with gates, and then I give you costs associated with each one of those things, and you have to select which one is the least expensive, right? The question is assumes that the decoder and the multiplexer are cheaper than the sum of their parts if you were to build them with gates, right? Okay. All right, so I think this is, let's see, this is the, okay, so we're almost to the end here. So this is something you might not have talked about in 211. This is something that I used to spend a lot of time on when I taught VLSI design. The idea of propagation delay. So you guys, I showed you how to build gates with transistors, and I talked about how transistors have 3 terminals, well, technically they have 4, but there's 3 that are important for the purpose of building up these logic gates. There's the gate, which controls whether the transistor is on or off, and then there's the source and drain, right? The gate is, by its very nature, a capacitor, because the principle by which transistors work is that the gate is a conductor and a dielectric and then a conductor. So it's a sandwich, right? The top is a polysilicon. The bottom is the channel, the semiconductor. And then when you charge up the gate, it attracts minority carriers into the channel, right, through inductance. Right, you guys with me? Okay, so what is the problem? Why is that important? Well, because you've got capacitance and the wires that make up the circuits that connect, the sources and drains and also connect together the gates, those all have resistance. So anytime you have resistance and capacitance, you end up with a time constant. That's the product, resistance times capacitance. The time it takes to charge up a capacitor is just the resistance times the capacitance. Is that easy? Yeah, it's that easy. Actually works out that way. This is the capacitance in farads and the resistance in ohms. You multiply them and you get charge time. Time. How long it takes to charge them up. Yeah, you guys with me? Now, there's also a time, by the way, once you've charged the capacitor of a gate, it takes the charge carrier's time to traverse the channel. It takes time for that, too. No one talks about that anymore, though. Why not? Because that was one of the big advantages of Moore's Law, was because with Moore's Law, it was shrinking the transistors down. That was shrinking the channel down. That made them switch, that sped them up because the charge could get from the source to the drain faster, because that channel was getting smaller. But anyway, for all of those reasons, gates have a delay. Input comes in, and so if you look at, now this is a timing diagram, and you guys are going to have to get used to reading these. This took me a while to get comfortable with when I was learning how to use this. But this is a plot where the x-axis is time. And each of these signals have a y-axis that represents high and low, right? So, for example, in this case, there's A. A is low, 0, false. And then at some point, it goes up to true, right? At what time? At this time. When it gets about halfway between false and true, that represents the time at which we considered it to have transitioned. You guys with me? Right? So what's that time? Well, you have to go all the way down to the time axis and figure out what time that happened. But it happened right here. But then what's supposed to happen is that it's a buffer. So if the input goes from 0 to 1, the output should go from 0 to 1, right? But in fact, it doesn't. It doesn't do it right away. It doesn't do it right away. It takes time. So if you look at the rising edge of A and the rising edge of Y, they're displaced in the y-axis. They're different. That is the propagation delay. You guys with me? Right? Now there's also a rise and fall delay, which is the slope of this line. But right now we're just concerned with the propagation delay through the gate. How long does it take for changes in the input to reflect in the output? That's the propagation delay. You guys with me? Okay, so now the book introduces this idea of contamination delay. This is actually, to be honest,